So a bottle rocket is modeled by the quadratic negative 2x squared plus 14x, where h is the height in feet after x number of seconds. So this quadratic model is the height after however many seconds you plug into the quadratic. How could we try and find when the rocket was 20 feet tall, or 20 feet high? How can we try that? How can we try to solve for that?
Jarvis.
All right, graph it. What were your thoughts?
There's a special type of handheld altimeter.
Okay.
Yeah.
So you use the tool?
Yeah.
Okay.
Cool. I had to do a project for rockets.
Well, we could graph the quadratic and look when it equals 20. That's one solution. Okay. For quadratic formula, though, what does the quadratic always have to be equal to? 0. If we were to set up this, to set it when it was equal, or when it was, to look for when that height equals 20, we know this quadratic model is the height. We're solving for when it equals 20, right? Can we still use quadratic formula for this?
Mm-hmm.
Yeah.
How?
Different time.
Oh, you could.
Right. What can we do to change this to 0?
Use this thing.
Multiply by 0.
I can just move this 20 over. So I have negative 2x squared plus 14x minus 20 equals 0. And then I can solve quadratic formula for that. Alright, so we can use quadratic formula. Do you think there's any other ways we could find when this quadratic equals 0 or 20? Complete the square that we used last week. As soon as we get it to this step, we can do complete the square. Any other thoughts? Factoring sometimes works, but yes, factoring is another way we can solve quadratic. What about this old school method?
On math.
I just made a table. That work?
Probably because you put it on there.
I mean, sometimes,
Say
depending
graph
on
it.
your decimals.
But it
So it
says
might be that like at 2.5 seconds. So 2.5 might not be on your table, so it might not always be on there, but tables could work. So we have a lot of different methods that we learn. As soon as we can set it equal to 0, we can use that quadratic formula to complete the square, the factoring. Those are all methods we learned. We could graph it and just see when does the graph hit 20, or we can use a table and see when on that table does our height equal 20. So these are all different methods we can use in order to find these types of situations. So thinking way back in the year, probably, I think it was right before Christmas break, so it would have been a while ago. We did something where we had multiple equations, and we were trying to find when these equations were equal to each other. So, for example, y equals 2x plus 3, and y equals negative 4x plus 8. We were trying to figure out when were these equations equal to each other. What did we call this?
math.
A while ago.
That's what you expect us to remember.
I can't remember what we had to practice. I had breakfast. I didn't have
So what did we call it when we had multiple equations?
PEMDAS. PEMDAS. Potato equation. Yes. Potato family.
So we call these systems of equations. So when you had multiple equations and you're trying to set when they were equal to each other, it was systems of equations. One of the methods we could try was graphing. We graph those equations until when they touched. We could also do substitution, where you solve for one variable and you substituted it into the other equation. And then the last one was elimination, where you set them sort of above each other and you crossed out a variable and solve for an elimination. I'm great at spelling myself. So, systems of equations, this is what we did in December. So we had these two lines and we were trying to see when were those lines equal to each other.
Is this when they touch?
Yes, and you're looking for when those lines touched.
Should it just?
Where they cross each other was the graphing. It was also represented by using substitution or elimination. Is this situation a system of equations? How? So I have one equation, is my quadratic. That's my rocket. My other equation is this line of 20 feet tall. This is my 20 feet. And where the rocket hits that line, those are the moments at which my rocket is at 20 feet. So we can use system of equations with quadratics as well, just like we could use with linear equations. So we call these linear systems of equations, but because we're now substituting one of these linear equations with a quadratic, we're now going to call them linear-quadratic systems of equations. So one of your systems of equations is going to be a quadratic, whatever that might look like, and one of them is going to be a line. And we're trying to see when do those lines and those quadratics touch each other. What do you think might be some differences from our old system of equations to our linear quadratic system of equations? What do you think might be some similarities or differences?
It's slanted.
Okay. But with our old system of equations, we have slanted lines too. So you might have something like that, where you had two slanted lines and we had to look where they touch.
There's a curvy bit.
Okay, so one of them is a quadratic. That's one difference. What else might be different? The quadratic can keep going. Okay. All right. Our normal system of equations, they only touch each other once. We had one spot where both of the lines were equal to each other. With your quadratic, though, we can get two. Just like a quadratic can have one y-intercept, or one x-intercept, two x-intercepts, no x-intercepts, a system of equations can have one solution, two solutions, or zero solutions. So it's possible to get two answers on these system of equations. Just like when you use your quadratic function, you get two solutions. When you use complete the square, we get two solutions. Or let's put those down. Okay. So for these system of equations, we're typically going to get two solutions, 2 points that we're looking for. I'll wait. You do put them down. Okay, I just take them all apart. All right, so let's look back at that example. So back at that modeling or that rocket question we looked at before, we said that we are looking for when negative 2x squared plus 14x, that rocket, we are looking for when that equals 20. How do you want to solve this? What can we do?
Graph it. Yeah.
Graphing is one way.
I think graphing is our best option.
Quadratic form. We said in order for quadratic formulas, though, everything has to be on one side. It has to be equal to 0. So we have to get this 20 over to our other side. So negative 2x squared plus 14x minus 20. So everything is on one side of my equation. How do we start the quadratic formula? What would we need to do?
With that A and B.
All right, so we have to figure out what my A, B, and C are. So A is negative 2, B is 14, and C is negative 20. Our quadratic formula We sing our little songs to ourselves. Opposite of b plus or minus square root b squared minus 4ac
All
all
over.
over 2a. So we have our quadratic formula. What now?
Shall we?
Substitute my numbers in. So plugging in my a, b, and c. All right, so opposite of b is opposite of 14, so negative 14, plus or minus the square root of b squared, so 14 squared, minus 4 times a, which is negative 2, times c, which is negative 20, all over 2 times negative 2. So I've plugged in my points in my quadratic formula. What should I try, or what do I want to focus on next? Now that I got all those numbers plugged in. Square root. All right, so we want to try to simplify what's under that square root next. 14 squared is 196. And then it's negative 4 times negative 2 times negative 20, which if we multiply all that together, thank you. Multiply all that together, we get negative 160. Once again, we want to watch out for those signs. So the negative 4 times a negative 2 gives you a positive 8 times a negative 20 gives you a negative 160. So always watch out for those signs, make sure we're paying attention. And then 2 times negative 2 is negative 4. What next? All right, my 196 minus 160. 196 minus 160 gives me 36. Minus 4. Square root 36 gives me negative 14 plus or minus 6 over negative 4. And then we'll get two problems because it's plus or minus. Yes. So one where it's negative 14 plus 6 over negative 4. And then negative 14 minus 6 over negative 4. So negative 14 plus 6 gives me negative 8 divided by 4, which is x equals 2. And then negative 14 minus 6 is negative 20 over 4, or negative 4, which is x equals 5. So the 2 points bring it all the way back to our question. The 2 points on when our rocket is going to hit that 20 feet. It's going to be at 5 seconds and 2 seconds. So once again, quadratic format isn't the only method. If you really like to complete the square from last week, you can use complete the square. If you prefer graphing, we can always try to graph it using your calculator, using your pencils, paper. If you like factoring, factoring works. Factoring isn't always perfect though, because there's some times where we ran into those quadratics that weren't factorable if you had the decimal answers. This one would have been factorable because we had nice whole numbers, but sometimes your answers are like 2.38 and you can't factor that. So sometimes we can't factor, but that is another method we can try. Questions, concerns about this question? The main thing, whenever we deal with a linear quadratic system of equations, we just need to take those two things and set them equal to each other. Take those two functions, take those two equations, set them equal to each other. So we set 20 equal to our quadratic, get everything to one side, and then just solve using one of your methods. Complete the square, quadratic formula, factoring, whatever you prefer. I don't care which method you use, you just need to use one of them. So we have a stock has a value that's modeled by the equation f of x equals 2x squared minus 14x plus 30. And another stock value is modeled by the function or the equation f of x equals 5x minus 5. So at what points would these stocks be the same value? How should we set this up?
opposite be
What are we looking for first?
the answer?
We want to replace the X.
We're looking for when they're going to be the same. What's another word for the same?
Similar.
Equal. So we're showing when are both of these equal to each other. So that means 2x squared minus 14x plus 30. We're seeing when is that equal to 5x minus 5. So how do I solve this? Whenever we do quadratics, we need to get everything to one side. It doesn't matter which side you get it to, just everything needs to go to one side. So I already have the majority of my stuff over here, so I'm going to move this 5x and this minus 5 over here. But how can I move this over there? What would I have to do?
Like,
5 plus 5.
Alright, so I can subtract 5x. Okay, we always need to pay attention to those like terms. So if I'm subtracting a term with an x in it, I need to make sure it's subtracting from another term in an x. If there's no like term, then I can just add it on in there, but we always need to pay attention to those like terms. So my 5x and my 5x, let's stop throwing things, please.
Sorry. Give me
And
the
so
attention.
negative 14x minus 5x gives me negative 19x. And then same idea with the 5. I can just add 5 to both sides. And so I have 2x squared minus 19x plus 35 equals 0. So always take those two starting equations, set them equal to each other on opposite sides of the equation. Get everything to one side, and then from here, it's just a quadratic that we've dealt with before. So you can choose complete the square, quadratic formula, factoring. Sometimes factoring works, sometimes it doesn't though. What method would you like to try on this one? Quadratic formula. That's the method that most students preferred last year. I know there were a couple students that enjoyed complete the square more than quadratic formula, but you can use quadratic formula, so that's opposite of b plus or minus square root of b squared minus 4ac all over 2a. So what terms would I have then? You can.
He's sad. No, he's just sad.
he is
Jarvis is doing such a great performance.
Alright, let's just put things away, please. You don't have to touch everything on my desk.
I was fixing your pens.
Wait, put them away, you don't need them right now.
Give me the attention, Jarvis.
You're no better.
I haven't done anything to disturb you today.
Covering yourself in tissues.
It's not disturbing you, it's disturbing
Alright,
myself.
so depending on which method you choose, quadratic formula says we want to do A, B, and C. So 2, negative 19, and 35. Plug in. Positive 19 plus or minus the square root of negative 19 squared minus 4 times 2 times 35 all over 2 times 2. Once again, what part do we always focus on? Square root. We want to get this part first. Once again, everything here is under the square root. I think when we did our quadratic formula assessment, one of the mistakes I saw was people would only put this under the square root and then would leave that other part out. So we want to make sure all of that's under the square root.
What did he say about touching your microphone? I need to ask.
Negative 19 squared should give us, good, awesome, 361. And then negative 4 times 2 times 35 is negative 280. And then 2 times 2 is 4. From here, we can subtract that inside piece. And 19 plus or minus the square root of 361 minus 280. 81, awesome.
Jarvis, I'm hungry.
Can't help you there. You can wait a couple minutes and you'll eventually get to lunch.
More than a couple. It's
What's our
like
square root of 81? 9. So we have
16.
19 plus or minus 9 over 4. And then once again, split into two problems. So 19 plus 9 is 28 over 4, which gives you 7. And then 19 minus 9 is 10 over 4, which gives you 2.5. So we have these two x's. We have these two solutions. Thinking back to quadratic formula, or sorry, not quadratic formula, thinking back to systems of equations, when back in December, what did our answer always look like?
One answer?
So we had one answer.
Coordinates, there was like.
It was a coordinate point. We always had an x and a y. For this problem, I know I'm going to have two answers. And I have my two solutions of 7 and 2.5, but are these my final answers?
Yeah, no.
I don't know what the y's are for either of them.
Nope.
So just like with system of equations, when you solve for x, you had to plug it back in to get the y. We have to do the same thing. So we have x, we just need to plug it back in to get the y's. With systems of equations before, we could choose either of the equations. Which equations would you prefer to plug those y back into?
B.
Yeah. You want to do the linear system, you do not want to plug it back in that quadratic because that's just annoying. That has more x's and stuff like that. So basically from here, you would just take your 7, x equals 7, and x equals 2.5, and you would plug those numbers back in. So 5 times 7 is 35 minus 5, so that would be 730, would be one solution. And then plug 2.5 in for x, times it by 5, subtract 5, whatever that number is. I think it's 7.5. 2.5, 7.5. So once again, just like with our other system equations, you need coordinate points as your solutions. It's not just the x, it's not just those two numbers we get, but it's plug it back into that easier equation. And typically, your linear systems of equations should always be easier to solve than that quadratic system. Questions, concerns, comments? Once again, the main thing is just setting both of them equal to each other, getting everything all to one side, and then just choosing your method to solve from there. And then and most of it's just pretty much solving quadratics like we practiced for the past half of the year now. See if you can find the solutions to this first one. Set them equal to each other. Get everything to one side, and then just choose your quadratic formula, complete the square, whatever method you want to solve. See if you can solve this first one.
I study hall, my test.
Bye, Floyd.
See you later.